Thank you, Gonzalo. Yeah, so in fact, today's webinar will focus on the limitations and the perspective of ligand protein cofolding. So as you know, deep learning has really transformed protein structure prediction recently, and naturally there has been a lot of excitement about extending those methods to protein ligand cofolding with the hope to make some changes in computer-aided drug design. But despite the perception of the public at large that this project is largely solved, actually the accurate modeling of protein-ligand interactions remain a challenge for those approaches. And in this session, our invited speaker will examine those limitations in complementary perspectives, offering critical insights, but also future direction for the field. So our first speaker will be Dr. Janani Durairaj, who obtained her PhD at the Wageningen University and is currently a project leader at the University of Basel in Switzerland. I know that she is about to also become assistant professor in Lausanne in the very near future, Lausanne in Switzerland. So our research objective is to bring biochemical context to deep learning models for studying variability in structures and interactions of proteins. And this afternoon, she will give a talk entitled Have Protein-Ligand Cofolding Methods Moved Beyond Memorization? Thank you very much, Janani, and the floor is yours.
Thank you. Show my screen. I hope you can see my screen.
Yes, we can.
Perfect. Okay. Today I'll talk about recent publication from the group that have protein-ligand cofolding methods moved beyond memorization. This has recently been accepted in NSMB, so it will be out as a paper quite soon. Okay, so let's start with why, of course, everyone is so excited about deep learning in the field of protein structure prediction is because quite a lot built on AlphaFold 2. AlphaFold 2 being the protein structure prediction method, which uses deep learning, got the Nobel Prize in 2024. And one thing that I'd like to quickly go over is how we as a community kind of how it felt when AlphaFold 2 came out. How did we know that we had actually a breakthrough in the field of protein structure prediction? So there were a lot of course, news articles, press releases, etc., that had plots like this when AlphaFold 2 came out, where essentially you would see like a big spike in performance, or if you measure error, then a big drop in error. And this was sort of seen as really saying that there was a huge increase in protein structure prediction performance. But always my favorite way of explaining this has been through this plot. So this is from the Critical Assessment of Structure Prediction CASP experiment. This is an experiment, a competition that happens every 2 years, where experimental structural biologists who solve structures of proteins have the structures that they've solved that they've not yet released into the PDB. These structures are sent, the sequences of the proteins from these structures are sent to predictors, so people who develop prediction methods to make predictions. And then the predictions are compared to the ground truth structures while neither the predictors have the answer or the world yet, so it's blind all around. And then we can actually see how does the field do on protein structure prediction when the answer is not yet known. And in this plot, you have 30 years of CASP. So every line over here is a year of CASP. And what you can see on the x-axis is actually the difficulty of the protein target to predict. So here, easy means that the sequence that was given for prediction, there is already a similar sequence with a solved structure in the PDB. Meaning that you could use homology-based approaches, for example, to transfer the structural information from the solved structure to the target structure, and therefore it's considered an easy target. While difficult means that this is a sequence for which there really hasn't been a similar solved structure in the PDB. And on the y-axis, you have the prediction accuracy. This is basically a metric where higher means that your prediction is closer to the ground truth structure. And what you might already notice is that if we had focused only on easy targets, Then this problem was kind of solved 30 years ago. So what really made AlphaFold 2 a breakthrough and what has really revolutionized this field is this performance across the board of being able to also perform well on difficult targets and not just easy targets for protein monomer prediction. So this is with AlphaFold 2. Okay, so this is sort of the basis of how we could benchmark such a method when it came out. And now we move towards protein ligand binding. So how do proteins and small molecules, their complexes, what do they look like? And here, of course, we reach a lot more complexity because you now have to simultaneously take into account the conformation of the protein and the pose of the ligand and the interactions that the ligand makes with the protein. One thing that we sort of saw out of the box is that already when in the AlphaFold 2 times is that you couldn't directly use AlphaFold 2 models for docking ligands. So yeah, I can show you a quick example. And this is maybe not so surprising actually, because AlphaFold 2 does not know that there's a ligand in there. So when it predicts the structure, it is not it doesn't have any reason to predict the structure in a way that the ligand would fit in there. And as you can see, a very small change in the structure can really basically block the pocket and not allow the ligand to bind. So we're talking about atom level interactions that really have to be extremely precise. And then since then, there have been the new generation of cofolding methods, so such as AlphaFold 3, Boltz, ProteinX, and now there's quite a few more. And these methods are actually deep learning methods that take as input both the protein sequence and the chemical description of the ligand, and simultaneously predict the complex of the protein and the ligand together. And so these are now the methods to benchmark to see if we have had a breakthrough in protein ligand complex prediction. And so my question at that stage was, what do we now need to be able to measure if we have this breakthrough? So how can we make this similar plot that we had with CASP for AlphaFold 2? How can we make this plot for these cofolding methods? So there's three things that we needed. So I'll go through them one by one. But in order to accomplish this, in order to make this, to collect all of the information needed to make this, I put together a consortium effort called PLINDR, the Protein Ligand Interaction Dataset and Evaluation Resource, which actually collects and harvests all of the protein ligand complexes from the PDB, annotates them for quality, consistency at the pocket and ligand levels, and also allows for comparing complexes with each other, which will become important as I will mention in a bit. Okay, so let's talk about what the three things that we would need for making this plot. So first, we need reliable ground truth. So what are the actual points, the targets that we are going to assess on? And here, since we're talking about atom level experimental accuracy, it becomes important to take into account the actual experimental data, because of course the experimental coordinates for protein ligand complexes deposited in the PDB are also models of the underlying electron density data. So you can have missing atoms because it's flexible there. You can have alternate configurations of ligands. For example, you could have a case like this where it's exactly the same protein, exactly the same ligand solved in two different structures. And if you had, for instance, this as your ground truth structure, but your model predicted something like this, then you would unfairly penalize it for something that is also correct and maybe in this case arguably more correct. So this was really important to be able to reliably trust the ground truth that we use for the benchmark. The second is the y-axis. So how do you know that your prediction is close to the ground truth? And here we had to actually develop some new metrics to determine this, because now we're no longer, I mean, while in the past there was a lot of effort in the docking direction where you just would compare the ligand pose. Here we're simultaneously predicting the protein and the ligand together. So we look now at the interactions between the ligand atoms and the protein atoms and check how similar are the interactions in the predicted structure compared to the true structure. So the distances between the ligand atoms and the protein atoms. And this is LDD-TPLI developed for the previous CASP. Okay, and then finally, probably the most important and the thing that needed the most thought is this measure of difficult. So this x-axis of how do we differentiate a difficult target from an easy target? Because as you already saw before, a lot of methods can already do the easy targets. And here, because we're talking about interactions between two different kinds of molecules, we start having different situations. You could have cases like this where the protein is the same, the pocket is the same, but the ligand is different. You could have cases like this where this is interesting, it's the same protein, but the pocket is different and the ligand is different. If you have a model that's been trained on this one, for example, would it now put this ligand in the same pocket, or would it correctly recognize that this is a different pocket? So all of these become difficult cases and different cases to deal with. And so what we went with is a measure of similarity between two complexes defined as the pocket coverage. So basically, is the pocket in the same place in the two complexes, and does the ligand make the same shape? And I'll demonstrate this better by example, where you have here, for example, you have two systems where it's actually protein kinases. And if you had looked at just the sequence identity of these proteins, it's quite low, but this is quite common, especially in enzymes where you have low sequence identity, but it makes exactly the same structure with the same pocket. And in this case, the ligand is binding in exactly the same way. So if you now use our metric of this is the shape, ligand shape similarity, and this is the pocket coverage, and now this is our combined similarity score, you would correctly see that this is an easy complex. If a model has seen this, it should be able to predict this. And similarly, on this side, you have a case where the ligands themselves, they have quite some difference. So the Morgan fingerprint or the chemical fingerprint similarity between these two seems like they're very different from each other. But if you look at the protein is the same, the pocket is the same, and the binding mode of the ligands is actually the same. So again, if a method has seen this, then it should be easily able to predict this. And here I just compare a little bit with commonly used metrics like sequence identity and Morgan fingerprint similarity that people have used in the past to try and say if a target is easy or difficult. And you already see that there are cases where you have low sequence identity but high protein ligand similarity, let's say. And similarly here where you can have so basically, we need to measure the similarity of the interactions and not the similarity of one or the other to really be able to judge difficulty. Okay, so we had all these 3 points finally, so we could make the plot. So we collected a benchmark data set called runs and poses, consisting of around 2,600 complexes released after the training cutoff of all of these cofolding methods. So after the training cutoffs of AlphaFold 3 and so on. And we made sure that these all have high quality so they could be trusted as ground truth. There are a lot of typical drug targets like kinases, MPRO, and so on. And of course, most importantly, each complex is annotated with difficulty, so the similarity to the training set that we can use to judge. Okay, so we had everything and then we made the plot, and this was the result. So here you have on the x-axis the similarity of the training set. On this side is easy, on this side is difficult. On the y-axis you have the success rate, so higher is better. This is incorporating LDDT, PLI, and RMSD. And yeah, as you can probably see, we have not really moved beyond this trend of memorization where you are able where these methods are really able to recover poses that have been seen before in training data but not really able to generalize to new pockets, new binding modes, new ligands. And just to stress again, this difficulty measure that I was talking about, it is a multiplication, meaning that even if the pocket has been seen before, if the ligand is new, it's considered difficult, and vice versa. And basically, if either one of the equation changes, then these methods currently struggle. Yeah, and this is just as a reminder. So essentially, we're kind of in the pre-AlphaFold era for this task of protein-ligand complex prediction. Okay, so then I just have some examples because something that sometimes comes up in this presentation is when you see this plot, is you might be thinking that, okay, so this means that if my complex is in this range, then I can trust these models, and if it's in this range, then I shouldn't. And while that's, I guess, on average true, as you can see, it's not so simple. So I just want to give some examples. These are cherry-picked, of course, but this is just to give you an idea of why memorization in deep learning models is such a problem, and why we really shouldn't we shouldn't have memorization in deep learning models. So here's some examples where from the different similarity bins. In the middle is the prediction always, and then you have the ground truth and the closest training system. So of course, when there is nothing in the training set that looks like this, then you just get an answer that's not reliable at all. Same here. But even in these two situations where you have a training system that's actually quite similar to the ground truth, you might have this kind of situation where, so now you see that the prediction is closer to the training system rather than the ground truth. And you might think that this is not such a big mistake, like most of the molecule seems correct. But in this case, actually, the chirality of this predicted molecule is wrong. So basically, the molecule that the model has predicted is not the molecule that was given as input. And this is a huge problem. Like chirality, all these small changes in atomic interactions, all of these have huge impact in downstream, especially like drug discovery campaigns and so on. So also here it's a similar example where you have this change because not necessarily because, but in the training system it's a different element here. So this is just to say that if a model doesn't learn underlying physical patterns that are responsible for such interactions, then it's really difficult to use it for downstream applications because you don't have the answer, and therefore you can't really trust that it's giving you the right answer, even if it's seen something similar before, because even a small change can actually change the answer. Okay, so then another thing we looked into is the physical plausibility of these poses. So basically, are the output molecules physico-chemically valid? And this is based on the PoseBuster suite. And you see that if you consider, in addition to just pose similarity, also physical plausibility, then you see a drop in performance. But excitingly, so Boltz 1x, it's one of Boltz 1 is a cofolding method based like AlphaFold 3. Boltz 1x is an extension of that uses this thing called diffusion steering to basically, instead of giving the default output of the model, it tries to steer the answer towards something that is physically plausible. And this has basically fixed quite a lot of the physical plausibility issues. And I just want to say, like, this is something available in Boltz 1x, but it's something that could be applied to any of these cofolding models. So I would say physical plausibility can seemingly be improved by this method. But this still remains independent of the memorization trend. So across all of the different similarity bins, you still have this drop in performance and this improvement in performance with Boltz 1x on physical plausibility, but it doesn't actually change the overall performance if it's a new pocket or a new ligand. And then the other thing that I quickly wanted to mention is confidence measures. So of course, all of these models, as with AlphaFold 2, start giving confidence scores to be able to judge how much you should trust their output. And we wanted to see if this confidence score would actually tell us that it's not performing well in the lower bins compared to the upper bins. So first we checked just for each complex, we generated 20 answers instead of one, and we tried to see is the one that is ranked on top actually the best rank, is the best scored model or not. And here what we saw is that it's true that there is something to be gained. So the blue is if you take the best scored of the 20, while the black is what you've been seeing until now, which is the top ranked of the 20. So there is some performance to be gained, but of course we wouldn't be able to choose this because we don't know the answer in a realistic use case. But what's a little bit more disappointing is that if you had just run one seed instead of 5 seeds, you get basically the same top ranked. So at the moment, it's not useful. It's not very useful to run more than one seed because you're still not able to actually choose the best answer anyway. So this is about choosing between samples for the same complex. What about choosing between systems? So can you use the confidence threshold to across the entire data set be able to say uh, this these systems I trust the answer and these systems I don't? Again, for most of the methods, it doesn't seem to be the case. So this is if you use IPTM to decide and then check the accuracy in each bin. But Boltz 1, which uses a slightly more complicated confidence model, does seem to have some filtering power, let's say, in this to be able to filter things where it's not sure from others. And you can sort of see it like this, that if you had filtered, what would this trend look like? Of course, the only issue is that there is no one, so all of these methods produce completely different ranges of confidences. So you cannot use like a 0.8, which would be a typical value for IPTM that you would imagine. You can't use this. And of course, if you use the optimal, then that's fit on this data set. So it's not maybe that clear if that's really useful. And by doing all of this filtering, you basically lose a lot of the data in each bin, but at least you would be able to know that these are trustable data. So at the moment, confidence is also not yet clearly usable for screening correct predictions from incorrect ones. Okay, so then how much can adding more training data help? So there's Boltz 2, which trains on 25,000 more PDB entries, so 2 years more PDB than Boltz 1, and unfortunately still has exactly the same trend. And as people use more and more training data, we start seeing that it becomes harder and harder to find difficult systems. So system is in the lower bin because, of course, a lot of the PDB repeats what has already been. Because yeah, there are a few really interesting drug targets that are solved with a lot of ligands very often. Okay, and then I don't know if I have a little bit of time to just quickly mention that we also compared with docking. So physics-based docking, and here we had to set up quite a lot of different ways of doing this because, of course, docking assumes that you already have the protein structure and you put the ligand in. So what we did was, of course, we checked redocking, which is the unrealistic use case that you just have the complex of the protein and the small molecule, you take the small molecule out and then you put it back in. This is useful to see the kinds of interactions that the data set has, but is not so practically useful because you don't have this answer of the protein and the ligand complex together. So then we also have homology modeling baselines and using the AlphaFold 3 structure as input to docking. And this is the results of that. So you can see redocking is shows that there is nothing essentially difficult about the complexes in the lower bins from a physical perspective. Like if you had had the correct protein conformation, then according to the force fields, the ligand fits in there quite naturally as across the other bins. But for everything else, so anything else where the protein structure needs to be predicted, we see the same trend. So essentially, the protein conformation remains the bottleneck here. Yeah, so just some ending thoughts is what's next for cofolding is there's always two camps, right? So there is the camp of can we just get more protein ligand complexes solved and then use that for training and will that fix the problem? Here I'm not so optimistic, as we already saw with Boltz 2. 2 years more training data didn't really help. Maybe if we have targeted campaigns that really get more diverse data, that could help. Another thing I think about a lot is what if we go back to the electron densities and try to get more information from there about the interactions there. But I do also believe that an equivalent push needs to come from the architectural side, that we don't necessarily have the model that will work for this problem yet. But at least now we have some evaluation measures, not just runs and poses, but also the kinds of metrics and similarity measures developed to be able to judge a breakthrough when it happens. Yeah, so this is where you can find out more about Plinder and runs and poses. There's CASP 17 that's going to happen now, and there's a call for targets and registration. So please look out for that if you're interested. And I'd like to thank my group. So this is the Picky Binders, and especially Petter, who led a lot of this work, and the ones who were circled here.